This is the 6th video in our series covering Lie algebras, and today we want to look at nilpotent maps, the very basics of weights and weight spaces, and something called the invariance lemma. Okay, so let's maybe start with the recollection of a special class of Lie algebras. And so given any vector space V, the set of all linear transformations, which we'll call GLV, is a Lie algebra where the bracket is defined as the commutator. And so maybe the canonical simple example for this would be n by n matrices. And in fact, if the dimension of V is n, then V is isomorphic as a vector space to Fn. In other words, all column vectors with entries from F that are size n. And then GLV is isomorphic to the set of all n by n matrices with entries from our field F. Now let's look at a definition, and this is maybe a linear algebra definition that you might have seen before. So if X is in GLV, so in other words X is a linear transformation from V to V, then we say that X is nilpotent if some power of X is equal to the zero map. So in other words, X to the n equals 0 for some n. And maybe you've also heard about nilpotence inside of rings or so on and so forth. So this is an idea which is across algebraic structures. Okay, so let's look at some examples of nilpotent maps. And maybe the canonical way to think about this is as upper triangular, or I should say strictly upper triangular matrices, and that's what we'll see with these examples. So notice if we've got the upper triangular matrix, which is 0A, 0, 0, so notice here A could be anything, then if we multiply that to itself, we get the 0 matrix. That's just by simple matrix multiplication. That makes this matrix right here nilpotent. So I'm underlining the A so that we can tell that it's not equal to 0. And maybe we could add that to the definition of nilpotence over here. We say that X, which is not equal to 0, is nilpotent if we have a power that's equal to 0. But I think maybe that's understood. Okay, so now let's look at this next example. So here we've got a 3 by 3 matrix, which is strictly upper triangular. And it's the most general 3 by 3 matrix. So notice we've got an entry A here, we have an entry B here, and we have an entry C here, and those could really be anything we want. And let's note that if we square this matrix, we get this matrix where the only entry is in the upper right-hand spot, and it's equal to A times C. So it's like we pushed everything up and right. And then if we cube this matrix, we get the 0 matrix. So that makes this matrix nilpotent. And so maybe the right way to think about this, like I said before, is nilpotent linear transformations are like a general way of saying that you've got a strictly upper triangular matrix. And that's because any linear transformation on a finite dimensional vector space can be expressed as an upper triangular matrix. And then it's only nilpotent if all of the diagonal entries are 0, making it a strictly upper triangular matrix. Okay, but we're not talking about linear transformations like in general. We should be talking about what's happening in a Lie algebra. So let's see if we can take this idea of a nilpotent map and then push it towards a Lie algebra framework. So let's recall the definition of the adjoint map, which is attached to any element of a Lie algebra. And we'll do this via the Lie algebra we're looking at today, which is GLV. So given any X in GLV, recall that means it's a linear transformation from V to V. Add X is a map from GLV to GLV. It's in fact a linear transformation, and it's defined by add X of Y equals the bracket of X with Y. In other words, XY minus YX. And our goal is to show that if X in GLV is nilpotent, then add X is also nilpotent. Okay, so let's see how we might do that. Well, let's suppose that we've got any y inside of GLV, and what we want to show is that some power of add x applied to y will give us the zero map. So we want add x to the maybe capital N power applied to y equals 0. The zero map, that is. So this is what we want. Okay, well, how might we do that? I think the best way to do that is to look at some powers of add x applied to y and see if we can see some sort of pattern emerging. So let's start with the first power. So add x applied to y, well, that's simply xy minus yx by definition down here. Now let's look at add x squared applied to y. Well, note that that is going to be x applied to xy minus yx, because we've got x applied to add x, or maybe add x of y. Okay, but then expanding this out using bilinearity, we'll get x squared y minus xyx, so that will be hitting this on the left by x. And then minus, the next thing will be xyx, and then plus yx squared. And that'll be hitting this on the right with x, just using the fact that we're doing the commutator here. Okay, but let's now combine like terms and note that we get x squared y minus 2xyx plus yx squared. Okay, so let's maybe take one more, one of these basic powers to see if we can see a pattern occurring here. So we'll take add x cubed applied to y. So that'll be the commutator of x with add x squared of y, in other words, this object. So x squared y minus 2xyx plus yx squared. Okay, well, that's going to give us x cubed y minus 2x squared yx plus xyx squared. That's multiplying this left entry on the left by x. And then we'll have minus x squared yx, and then plus 2xyx squared, and then minus xy cubed. All of those are from subtracting the multiplication on the right by x. But now let's combine like terms and note that we have x cubed y, and then minus 3x squared yx, and then plus 3xyx squared, and then minus yx cubed. But now let's look at these numbers. So here we've got a 1, a negative 2, and a 1. Here we have a 1, a negative 3, a 3, and a negative 1. Well, that looks to me like we've got binomial expansion. And that's exactly what we have. So let's start with that observation at the top of the next board and then go on. Okay, so in general, we'll have the following expansion of add x to the n power applied to y. So notice it's the sum as k goes from 0 to n of minus 1 to the k. n choose k, we have x to the n minus k times y times x to the k. And I won't prove this, but maybe proving this by induction will be one of the homework exercises. Okay, and let's note that we want to show that some power of add x applied to y is equal to 0. And we're given that some power of x applied to any vector is 0. So in other words, some power of x is the 0 map. So now we'll use that to prove our goal. Okay, so let's suppose that we have x to the n power is equal to 0 for, some natural number n. And then, well, what's a good choice for the power of add x to hopefully get 0? Well, looking at the fact that we're splitting the x's between either side of y, perhaps just double the value of n that makes x 0 will make add x 0. And that's in fact exactly what'll work. So let's do the following calculation to finish it off. So add x to the 2 times capital N times y, or evaluated at y, will give us, using this formula up here, the sum as k goes from 0 up to 2 times n, we have minus 1 to the k, we have 2n choose k, we have x to the 2n minus k, and then y, and then x to the k. Okay, great. But now I'm going to split this into two parts. So my first part will be the sum as k goes from 0 up to n minus 1. And so we'll have minus 1 to the k, 2n choose k. We'll have x to the 2n minus k, but since k is going between 0 and n minus 1, all of those will have a factor of x to the n. So I can pull that out front. So we've got x to the n, and now here we'll have x to the n minus k, y, x to the k. Again, notice if we multiply this x to the n through, we'll get x to the 2n minus k. And also, because here k is between 0 and n minus 1, we're guaranteed that that's like a non-negative power of x, which is important. Okay, now let's look at the rest of the terms. So that'll be the sum as now k is going from n to 2 times n, well, of the same thing. So we have minus 1 to the k, and then 2n choose k. We have x to the 2n minus k, y, and now x to the k. But now, since k is going from n to 2n, we can factor an x to the n out of the right-hand side. So I'm going to write this as x to the k minus capital N, and then we've got an x to the n going out the right-hand side. And let's put big parentheses around that as well. And again, because here k is between capital N and 2n, we know that this is a non-negative power of x, which is important. Okay, but then by our assumption of x being nilpotent via this number n, we know that this x to the n is the zero map. So if we apply the zero map to this thing right here, we'll get the zero map. And then this power of x to the n is also the zero map. So if we were to apply that to a vector, we would get 0. So in the end, 0 plus 0 is 0, and that does it. We have shown that add x is nilpotent. Okay, now let's move on. So we've been doing lots of stuff that makes Lie algebras look like other algebraic structures, rings, groups, etc., like first isomorphism theorem, ideals and quotient objects and stuff like this. But now we're dipping our toes into the structure inside of Lie algebras that makes them inherently different than those other objects. And that is starting with this notion of a weight. And I'm not gonna define the weight on this board, but this is towards that idea. Okay, so let's suppose that we've got a Lie algebra L, which is a subalgebra of GLV, where V is a vector space over F. So this makes this a Lie algebra over a field F. And then furthermore, we've got a subalgebra of L, which I'll call capital H. Then we've got a linear transformation, lambda, from H to F. So from that Lie subalgebra to the ground field. So if you recall, anytime you have a linear transformation from a vector space to the ground field, we say that that linear transformation is in the so-called dual space. And that's what we have right here. So lambda is inside of H star. That's the dual to capital H. Next up, we're going to define the following set. So we'll denote it by V lambda, and it'll be all vectors V and V, so that if we apply H to V, we get a number times V, but not just any number. It'll be lambda evaluated at H. And this is going to be true for all little h inside of H. So a lot's going on here. So notice that anytime you've got a linear transformation, which H is a linear transformation from V to V, given that H is a subalgebra of V. So we've got a linear transformation hitting a vector V, and then we get a number times the vector V. That makes this vector V a eigenvector of H, and it's got eigenvalue lambda H. But note that since this is supposed to hold for all H inside of the subalgebra, that makes this vector V an eigenvector for every element of the subalgebra. And what this lambda is doing is it's encoding the different eigenvalues that come out of this eigenvector-eigenvalue relationship, which is happening over and over and over again. Okay, so now let's prove a claim related to these spaces. And that claim is that V lambda is a subspace of V. And we're going to prove this just using the definition of a subspace. So it should be closed under taking linear combinations. And then all of the other parts of being a subspace really follow from that. Okay, so let's suppose that we've got two vectors. I'll call them V and W inside of V lambda. And we've got two numbers. I'll call them alpha and beta inside of the field F. And what we want is for alpha V plus beta W to be inside of V lambda. But we've got a rule in order to get inside of V lambda, and that is it has to satisfy this thing over here. Okay, so then let's take some arbitrary H inside of H and make sure this happens. Okay, so let's look at H evaluated at alpha V plus beta W. But H is a linear transformation, so we know that we can maybe factor it across linear combination right here. So here we're going to get alpha H applied to V plus beta H applied to W. But then V and W are inside of V lambda, so they satisfy this rule over here. So here we have alpha lambda H times V, and then plus beta lambda H times W. Okay, so I'm gonna underline some stuff in orange, and this is simply a number times V, and this is also simply a number times V. The alpha and the beta are the numbers that are weighting our linear combination right here, and then the lambda H comes from the fact that lambda takes elements of H just to numbers. But notice we've got a greatest common factor, or a common factor, I should say, of these two terms, and it's this lambda H term. So we can factor that out. And so here we'll have lambda times H times alpha V plus beta W. But if you look over here at the rule that alpha V plus beta W has to satisfy to get inside of V lambda, you'll see that we have satisfied that rule. So in fact, yes, alpha V plus beta W is inside of V lambda as needed for this to be a subspace. Okay, so now let's move on. So now we need a new definition. So we'll say that lambda inside of H star is a weight if V lambda is not the zero vector space. So if you look at this definition of V lambda up here, it might seem quite restrictive because all of these vectors have to be eigenvectors for every element of the subalgebra, and that seems like it may not always be doable. So it seems like you're likely to get the zero vector space. And so that's why we want to give this name a weight, or we want to give this lambda that gives you the non-zero vector space a special name, and we'll use the word weight. Okay, so now let's look at an example. So let's take H to be all upper triangular matrices with entries in a field F. And then they're going to be 3 by 3 upper triangular matrices, although this can be generalized pretty easily. And so notice that's going to be a subalgebra of GL3F. So that's just all 3 by 3 matrices with entries in the field. That's playing the role of L over here. And then that's equal to GLF3. And so F3 is playing the role of V over here. So what we'd like to do is find something that is an eigenvector for every matrix of this form. And you don't have to try too hard, and you'll see that the maybe standard basis vector E1 is an eigenvector for all matrices of this form. So let's check that. So let's take a matrix of this form. So we're calling it RST 0UV 00W. And let's multiply it into the standard basis vector E1, in other words, 1, 0, 0. And by straightforward matrix multiplication, you get R0, 0, which is R times 1, 0, 0. But since this is like an expression for everything inside of H, that means this E1 is an eigenvector for all of these matrices. So let's write that down. So E1 inside of F3 is an eigenvector for all little h inside of H. And then we can use this to get an idea for how we should define our function lambda, or our linear transformation lambda. So let's see, we'll think of this as playing the role of H, and then this number right here should be playing the role of lambda of H. But that's just simply extracting this number r from the matrix. So let's do that. So let's define lambda inside of H star by lambda evaluated at the matrix RST 0UV 00W to be the number r. Great. And then under this setup, we see that V sub lambda is, well, equal to all vectors V satisfying this rule. So that's just all multiples of E1. So we might as well write this as A00, as A runs through all elements of F. So in other words, it's the span of the vector E1. And you can check that nothing else is inside of this V lambda if you wanted to. Okay, let's do another example. So for our next example, we'll think about SL3. So that's all 3x3 matrices with 0 trace. And we'll take the subalgebra to be all diagonal matrices of that form. So in other words, it's diagonal 3x3 matrices with trace 0. And so it's pretty easy to find a basis for H in this case, and we'll call that basis H1 and H2, where H1 is this matrix here, 1, 0, 0, 0, negative 1, 0, and then the rest zeros. And then H2 is this matrix right here, which has a 1 here and a negative 1 here, and then zeros elsewhere. Okay, so now let's look at H1 and H2 applied to arbitrary three-dimensional vectors just to get an idea of what's going on with them. So I'll write H1 here. So 1, 0, 0, 0, minus 1, 0, 0, 0, 0. And we'll write an arbitrary vector here. I'll reuse A, B, and C as the numbers. Okay, so let's notice that this gives us A, negative B, and then 0. I think that's just pretty clear by matrix vector multiplication. And then here we'll have H2, which is, 0, 0, 0, 1, 0, 0, 0, minus 1. And here I'll x, y, and z for my numbers. So let's see, by matrix vector multiplication here, we'll have 0, 1, or sorry, 0, y, and then negative z. And then from this, we can get an idea of what the eigenvectors and eigenvalues are for each of these. And so let's spread it out for this one. So let's notice that E1, which is the vector 1, 0, 0, is an eigenvector for, well, in fact, it's an eigenvector for both of these. It's an eigenvector for H1 with value of 1, and it's an eigenvector of H2 with eigenvalue of 0. And you can see that just by direct calculation. And then maybe we'll redo this with E2. So this is an eigenvector. In fact, it's an eigenvector for both. So it's an eigenvector for H1 with a value of negative 1. So I think that's pretty clear by direct calculation. And it's an eigenvalue for H2 with a value of positive 1. And again, just by direct calculation. And then E3 is also an eigenvector for both. So this is an eigenvector for maybe H1 with value of 0 and H2 with eigenvalue of negative 1. Okay, so I think that's a pretty nice description of the eigenvector-eigenvalue relationships between the standard basis vectors and well, these h1 and h2 elements of H. So now we'd like to define, well, we'd like to at least get one example of a weight here. And in fact, these three boxes right here give us three maybe standard ways to write down weights in this case. Maybe we'll just focus on this first box and I'll let you do the other ones on your own. So let's define lambda from H to F by lambda of H1 is equal to 1 and lambda of H2 is equal to 0. But in that case, we have V sub lambda is equal to the span of the vector E1, based off of, well, this eigenvector-eigenvalue relationship along with the way that we defined lambda. And then, well, we could maybe call this lambda 1 if we wanted to, and then you could define a corresponding lambda 2 and lambda 3 based on that. Okay, good. So let's move on to like maybe the big result for the video. Okay, now for something called the invariance lemma. So let's say we've got a Lie algebra L, which is a subalgebra of GLV, over a field of characteristic 0. So we've got our base field that we've been working with, and that's been arbitrary before, but now it has characteristic 0. We also have I, which is an ideal of L, and we have lambda, which is a weight, and lambda is an element of I star. So in other words, it's a linear transformation from I to the base field F. Then the weight space V lambda, which I guess we didn't call this a weight space, but that's the name for it. So V lambda is a so-called L invariant subspace. So what does that mean? Well, that means if you've got a V inside of V lambda and you've got an X inside of L, then if you apply X to V, you stay inside of V lambda. So that means that L just loops everything from V lambda back to something in V lambda. Okay, so let's see how this might go. So we want to suppose that V is in V lambda and X is in L, and like I said before, hopefully get that XV is inside of V lambda. But in order to do that, we need to involve something inside of I. So I'll take H inside of I. And then, well, let's see how to do this. So let's look at H applied to XV. So here we're using the fact that in order to be inside of V lambda, we have to have this rule where when you apply H, it's the same thing as applying lambda and doing all of this other stuff. So that's why we're applying H to this XV, because it has to satisfy the rules to be inside of V lambda. Okay, but then by associativity here we have this is HX applied to V. Recall that V is a vector, but H and X are both linear transformations on V. But now we can do a little bit of a trick and rewrite this as XH and then plus the commutator of H with X applied to V. And this is just as straightforward as adding 0. That's because HX is simply HX minus XH. And so notice everything would cancel just back to that XH. But since we're inside of a Lie algebra, this bracket is an important thing to look at. But now let's expand this out, and we have X applied to H, which has been evaluated at V, plus we've got this HX evaluated at V. So something like that. But since V is inside of V lambda and H is inside of the ideal I, well, we can use, the definition of V lambda to simplify that bit right there. So notice this is going to be lambda applied to H, and then this is multiplying into X times V. Again, because V is inside of V lambda. And then this right here is going to be lambda applied to HX applied to V. And well, why is that? Well, that's because we've got an ideal here. And since H is inside of the ideal, we know that this is also inside of the ideal. Okay, great. But that means V will be a eigenvector for things inside of the ideal, but it's got this other number in front of it. Okay, so let's note that this term right here is what I'll call good. So this term right here is good because we started with an h on the left and we've got a lambda h on the left. This term over here is maybe what I'll call bad. It's not really bad, we just need to take care of it. And that's because here we started with an h on the left and we ended with a lambda of the bracket of h with x. But how could that badness disappear? Well, that badness could disappear if this thing was equal to 0. So I'll just put that we want this to be equal to 0. This lambda applied to the bracket of h with x. Okay, so let's see if we can show that. Quickly recall where we are. So we had a v and v lambda, an x and l, and an h in I, and our goal was for xv to be in v lambda. And recall that that would follow if we showed that the bracket of h with x, and then, well, applying lambda to that bracket, gave us 0. So that's how we'll finish this proof, is by showing that that is indeed 0. And we'll do it by looking at a certain subspace of V, and we'll call this W. So let's say W is the span of, well, it'll be our vector V that we started with here, and then it'll be the vector x times V, the vector x squared times V, all the way up to the vector x to the n times V. And you might say, well, how do we know we can stop somewhere? Well, we can stop because, well, we're in a finite dimensional vector space. So I think I forgot to write that here, but let's write here that the dimension of V is less than infinity. So we're in a finite dimensional vector space. So that means that, well, we can't have an infinite dimensional subspace. And then, well, that means that also if we were to add one more, so we're stopping one short of, if we added one more, it would be linearly dependent. And then because of that, it follows that this set right here doesn't just span, it's also a basis for W. Okay, good. And then maybe we'll call that basis for W, script BW. Okay, nice. And now let's suppose that we've got a new y inside of our ideal I, and let's make the following claim. And that claim is, if we look at the matrix representation of y in this basis of W, which we've expressed, then we get an upper triangular matrix, and on the diagonals is lambda evaluated at y. So I'll just put lambda evaluated at y, ... all the way down the diagonal. And then above the diagonal is free, and below the diagonal has to be equal to 0. Okay, and then how can we prove this statement? Well, we're going to prove it by induction on the columns. And that induction will go left to right on, like I said, the columns. And let's observe that our base case will be, well, it's going to be the leftmost column, but it's actually done in the leftmost column, because notice that y evaluated at V is equal to lambda y evaluated at V. But then we can extend that out to plus 0 times xv plus 0 times x squared v plus 0 times x to the nv. And that'll be all of those zeros that are in the column below lambda of y. Okay, so again, that follows because v is in v lambda and y is an element of that ideal, which we're building out of lambda, or lambda is like related to. Okay, so that's the base case done. And now let's make an induction hypothesis. So that'll be, suppose the kth column is, well, what I'll call good. In other words, it's of that form. But the kth column being of that form means that y evaluated at xkv is only expressed with powers of x that are k and lower. Well, that's really what this means to be upper triangular. Well, with respect to this basis. So in other words, it's equal to alpha naught times v plus alpha 1 times xv all the way up to alpha k minus 1 times x to the k minus 1v, and then plus lambda of v times x to the kv. So that's our induction hypothesis. Okay, so now let's maybe bring that to the top and keep going. Okay, so towards showing that that matrix had the correct form, we made the following induction hypothesis on the action of y on x to the kv. And this was really an assumption that the kth column had the correct form. And now we're going to consider, well, really the structure of the k plus first column, which is really looking at y evaluated at x to the k plus 1v. So if we can figure out what y does to that, we know what the k plus first column looks like just by the matrix representation of a linear transformation from, linear algebra class. Okay, so factoring some things out, this is the same thing as yx applied to xkv. But now we can rewrite this yx using the commutator, similar to what we did before, and this will be equal to xy minus the bracket of y with x applied to xkv. So something like that. But now we know what xy applied to xkv is because, well, we know this rule right here. So let's write that bit first. So that's going to give us something like this. Alpha naught xv, because we've got this extra copy of x from this right here, plus alpha 1 x squared v added all the way up to alpha k minus 1 x to the kv, and then finally lambda v x to the k plus 1v. But that's just from this first term. So next up, we'll have this minus bracket xy applied to xkv. But now we're going to use the fact that we had an ideal here. So since I was an ideal and y was an I, we know that xy or bracket xy is also inside of I. But notice that bracket xy is hitting x to the kv. So we can apply the induction hypothesis to that because y was essentially an arbitrary element from I. So we're just replacing y with bracket xy. So again, since bracket xy is inside of I, we apply the induction hypothesis to it. And that'll give us bracket xy applied to x to the kv. Well, it expands in this form, but with different numbers, of course. And that'll be something like this. We'll have beta naught v plus beta 1 xv all the way up to beta k minus 1 x k minus 1v. And then finally, plus, we'll have lambda of bracket xy and then xkv. So something like that. Okay, nice. But now what we can do is smush this into, well, this right here, because, that's essentially what we did. We extracted that bit and then maybe like expanded it again using the induction hypothesis and the fact that I was an ideal. Okay, so putting all of that stuff together, we get the following expression for y times, well, xk plus 1 times v. So let's write that down. So y xk plus 1 times v will now be equal to something that I'll call gamma naught v plus gamma 1 xv, ending all the way up to what I'll call gamma k xkv, where let's take a minute to note that that gamma k is a combination of, well, this number right here, which is lambda evaluated at xy, and let's see, this number right here, which is our alpha k minus 1. And then after that, we'll have this last bit, which comes from this right here. So that'll be lambda v times x to the k plus 1 v. But this is exactly the form that we needed for the k plus 1 column to have the right shape. So that implies that the k plus first column is also good. In other words, it's in the right shape. So that finishes that inductive argument that we have that maybe upper triangular structure for our matrix representation of y. Okay, so let's see where that takes. Okay, now we're ready to start putting everything together. Let's briefly recall that x was an element of L, v was in v lambda, and h was in I. And recall that if we could prove that lambda evaluated at the bracket of h with x was equal to 0, then that would imply that xv was an element of v lambda, completing the proof that v lambda is an L invariant subspace. So we had this tool, this vector space tool W, in order to do that. And W was the span of v, xv, x squared v, up to xnv, where we stopped that short to make it a basis. And we called that basis b sub w. And we just finished proving that if we had any element of y inside of the ideal, its matrix expression in terms of bw was upper triangular, with the diagonal being just all lambda y. And now let's maybe look at the following observations, which are pretty clear. So let's notice that W is X invariant. So what I mean by that is if you take any element of W and apply X, you get another element of W, and that's by construction. So we constructed W to have that property. Okay, and then let's also notice something else, and that is W is H invariant. And that may not seem totally clear, but notice that this Y just comes from the ideal, and our original H comes from the ideal as well. So that means the matrix representation of H like this also has this form, this upper triangular form. But that keeps everything inside of W as well. So this invariance just comes from the fact that H is inside of I, and by this line that we just proved here. Okay, so now let's set Y equal to the bracket of H with X. And notice that W is going to be Y invariant here. And that's because Y is inside of the ideal, because, well, H is inside of the ideal and we have an ideal. But that means if we take the matrix representation of Y, it'll have that form over there. So that means that the trace of Y will be equal to n plus 1 times lambda Y, because that's an n plus 1 by n plus 1 matrix. Okay, but then on the other hand, the trace of Y is the same thing as the trace of the bracket of H with X, but as we've seen in previous videos a couple of times, the trace of a bracket is always equal to 0. So we have this is equal to 0. But then let's put this together. That tells us that n plus 1 times lambda y is in fact equal to 0. But since we're in a field of characteristic 0, that tells us that lambda y is equal to 0. But notice that y was the bracket of h with x. So the bracket of h with x, lambda applied, is equal to 0. But that was the last thing that we needed to prove to finish the proof that we do have an L invariant subspace. Okay, now I'm going to leave you with some exercises. Here are two nice exercises. So the first is to fill in that little gap that add x to the n evaluated at y gives you that expression that we used in the proof. The next proves, well, that such a lambda defined over here really has to be a linear transformation. We defined it in terms of being a linear transformation, but you might think, well, could it just be any function? And it can't. So let's look through this. So let's suppose that L is a subalgebra, a Lie algebra, which is a subalgebra of GLV, and it's got a subalgebra H. And then mu is a function from H to F, not necessarily a linear transformation. But it does satisfy this rule that the following set is non-zero. So all vectors v and v such that hv is equal to mu hv for all h and h, that's not the zero vector space. And then we want to show that that implies that mu is a linear transformation. Meaning that, well, we could really take the necessity of being a linear transformation out of this because it follows, well, at least in the definition of a weight down here. And that's a good place to stop.